Hello, everyone. Thank you for participating in the VCS methodology webinar. This webinar is to provide an introduction to the recently approved methodology VM0022. This is a methodology for quantifying nitrous oxide emission reductions from reduction in nitrogen fertilizer application rates in U.S. Agricultural crops. Before I get into the agenda for today, I'd like to introduce the participants on the webinar. I'm Aditi Sen. I'm the Methodologies Manager at VCS, and with me is my colleague Ben Block. Also on today's webinar is Adam Diamant, who is with EPRI. EPRI played a key role in supporting the development of the methodology. From Michigan State University, we have Phil Robertson and Neville Millar. Michigan State University was the principal methodology developer for this methodology. And finally, from Environmental Services, we have Sean McMahon and Richard Schroff. ESI was one of the validators for this methodology. So let me give you a quick overview of what we will cover in today's webinar. I will provide a very quick overview of the methodology. We will then hear from Adam with respect to EPRI's role in the development of this methodology. Neville will then provide an overview of the key elements of the methodology. Finally, we will hear from Sean about the key issues to look out for when validating and verifying projects that are developed under this methodology. We will also have a Q&A session at the end of the webinar. We will be taking questions throughout the webinar, so please send us your questions through chat. You will see a chat box on the software, GoToMeeting software, and my colleague Ben Block will be moderating the Q&A session. We will also be recording the webinar and posting this on the VCS website in a week's time. This is one of the 3 agricultural land management methodologies that have been approved under the VCS. It is a very important methodology. As many of you know, emissions from nitrous oxide and from emissions particularly from the application of fertilizers are a significant source of emissions in the agricultural sector, particularly in the U.S., where farmers have typically overapplied fertilizer. This methodology provides a pathway for quantifying the carbon benefits of optimizing fertilizer application in agriculture in the U.S. And it is unique because it offers a flexible pathway. It allows project proponents to either use simple IPCC defaults or use tier 2 factors, which have been empirically derived based on some of the scientific work that's been done by Michigan State University. The methodology was developed by MSU with support from EPRI, and the methodology was assessed independently by 2 validators. The first assessor was ESI, and the second assessor was DNV. With that, I'd like to pass this across to Adam, who will talk about EPRI's engagement in the process.
Thank you, Aditi. I very much appreciate the opportunity to present today. My name is Adam Diamant. I am a technical executive in EPRI's Energy and Environmental Analysis program. Before I get started, I just want to thank the VCS for the opportunity to present today, as well as working with us over the last several years to finalize the methodology and put it through the methodology review process. And I really appreciate the assistance that the VCS staff has provided, as well as the support from MSU and all of their work on this project, ESI and DNV as well. So with that, let me start by first saying who EPRI is and why we're involved in this effort. For those of you who aren't familiar with the Electric Power Research Institute, EPRI, we're a nonprofit 501c3 scientific research organization that was created in 1973 to basically perform objective research and development activities related to all aspects of the production, transmission, and use of electricity, including the environmental impacts of the use of electricity. And we have about 450 participants or member organizations around the world in 40 countries. And about 90% of the electricity that's delivered in the United States is delivered by member companies who are part of the EPRI membership in some capacity. And as you'll see on the slide, we have principal locations around the country in Palo Alto, California, Charlotte, North Carolina, and Knoxville, Tennessee. Can I have the next slide? Thank you. So many people have wondered what EPRI's involvement has been in the development of offsets and in offset policy. Basically, we've been involved in 3 areas of offsets. First, we've focused quite a bit of our work on evaluating the potential for new types of large-scale, low-cost emission offsets, and have focused our research activities on trying to bring those areas that we've identified, those offset project types, that other parties aren't really working on or weren't working on when we started them, and bring them to fruition. And 2 areas we focused on specifically for many years now have been the development of nitrous oxide emission offsets that you'll hear about today, as well as the development of reduced emissions from deforestation and degradation, or RED, another area we at EPRI have been very active about. We've also been quite active trying to educate stakeholders, policymakers, industrial participants, offset project developers, etc., about offsets. And in doing that, we have held 13 offset workshops over the last 6 years and invited multiple stakeholders to participate in those, and talked about different areas of offsets, issues related to offsets, technical issues as well as policy issues. And we've provided a number of reports that we've developed at EPRI as well that we've published. And all of that material from our offset workshops, including expert presentations, background paper, and all of our reports that we've written over the last almost decade now on offsets, are available on EPRI's website, on the website shown here at the bottom of the slides. Also, we've done a lot of work in recent years at EPRI on doing actual quantitative analysis of potential future offset supplies, and we're right now just finishing up a large report that looks at potential offset supplies around the world in 200 countries and 65 sectors. And that's work that will be forthcoming, and when it's released later this year, it will be publicly available as well. Next slide, please. So when we approach the idea of doing offsets in nitrogen management, specifically reducing nitrous oxide emissions from fertilizer use in crop production, there were a number of benefits we saw to doing this that really made this methodology one that we wanted to pursue, and to pursue the underlying science to see if it would be possible to develop a methodology that could potentially provide offsets to farmers who could reduce their fertilizer use. So first off, reducing fertilizer application in crop production can reduce nitrous oxide emissions. That's well known. And the work we did, which I'll talk about in a minute, is about doing some scientific research work on farms in Michigan to verify that that could be done, and to understand the underlying scientific processes by which that could be achieved, and to be able to quantify emission reductions that would occur from reducing nitrogen fertilizer use, particularly in corn production. A nice thing about nitrous oxide emission reductions in agriculture is that they're permanent and that there's no saturation. This is a problem. Permanence, as many of you know, is a problem for other types of offsets in ALM categories as well as in forestry, where for whatever reason emissions can be reintroduced into the atmosphere after a project is completed. In contrast, by reducing fertilizer use, the N2O emissions that would have occurred are permanent. They take place immediately when the fertilizer is not used, and there's no saturation, meaning they can be done over time, over and over again. Also, the way that we've developed our protocol and the approaches that we've proposed to be done to reduce nitrogen fertilizer use on farm do not cause leakage. These approaches do not cause a reduction in crop yields, which would be the driver for leakage and activity shifting. And the way that we have accomplished achieving fertilizer reductions on farms with this methodology, or the way that the methodology works, makes sure that that doesn't occur. Also, one of the terrific things about this kind of approach is that it can be done across a very wide range of crops and geographic regions, both here in the United States and internationally. the initial focus of our scientific research work was done in the north central region, which is essentially the U.S. Midwest and a few other states, comprises 12 states in the region. And the reason we focused in that area, which we'll talk about in the next slide, is because most of the corn production in the United States occurs in those 12 states, and most of the nitrous oxide emissions from fertilizer use emanate from the growing of corn in that region. At the same time, we wanted to create a methodology that would be widely applicable across the United States to a wide range of crops and in a wide range of conditions. And we've done so with the VCS version of our methodology that applies to both a particular method that Dr. Millar will talk about that's used in the north central region for corn production, and another alternative method that can be used to quantify and obtain greenhouse gas emission offsets by achieving nitrous oxide emission reductions in other crops grown across the country and other crops grown outside of the north central region. Also, the approach that we've developed basically can be done by farmers very cheaply. It can be done at very, very low cost, virtually very few hard costs for farmers to actually implement this technology. Essentially what they're doing is they're using less fertilizer, and so they have to pay a less amount of money for fertilizer that they use and potentially fuel and labor that's associated with applying fertilizer to the land. So we think that this will help in terms of farmers being able to change their common practice and adopt a new approach to achieving greenhouse gas emission reductions. And then finally, there are a number of ancillary co-benefits to reducing nitrogen fertilizer in the environment. First off, nitrogen typically has two pathways to go into the environment when it's used in excess of what a crop needs to reach its optimal yield. It can be emitted into the atmosphere through volatilization as nitrous oxide, and that's what our methodology is specifically focused on quantifying. But it also can be released into the waters through leaching as nitrate and cause pollution of water resources. So one of the key ancillary benefits of this particular methodology and the approach that farmers will use to reduce their nitrous oxide by using less fertilizer is there will be less concomitant water pollution as a result. And we view that as a very important benefit of the methodology. In addition, there are other pathways that Dr. Millar will talk about by which excess nitrogen gets into the environment. And the role of excess nitrogen in the environment is very important. And this particular protocol is provides a good opportunity to basically reduce overall reactive nitrogen in the environment, whether that's in the air, the water, or the land. And those are benefits that are co-benefits. Emissions from fertilizer use are very large in the United States, and very large particularly in the Midwest. Annual emissions from soil are about 200 million tons CO2e. It's about 3% of total U.S. greenhouse gas emissions. And corn is basically the most intensive user of fertilizer in the country. And 80% of corn for grain is grown in the 12 states of the north central region. As you can see on the table in the right, this is acreage of planted corn around the country in 2009. And if you look through there, you'll see that the largest corn production is being done largely in the states in the north central region, places like Iowa, Illinois, Nebraska, Minnesota, etc. And so our project focused initially on creating emission reductions by reducing the quantity of fertilizer used to grow crops, particularly in those 12 states. But also, as you'll hear a little later from Neville, our methodology applies across the entire country. Can we get the next slide? So why did we partner with MSU? So there are many reasons for this. One of the most important is the picture on the right. Phil Robertson and Claire McSwiney had published a scientific piece in the literature in 2005 that I took notice of that showed this very interesting graphic of the yield of corn being essentially a very hyperbolic function when graphed, the nitrous oxide emissions being a hyperbolic function as a function of the yield of corn. And one of the interesting implications of this graphic is that you could reduce the use of nitrogen just a small amount and reduce the yield infinitesimally, basically, and change dramatically the amount of nitrous oxide emissions. And this was original work that Phil and Claire had done at Michigan State. And we decided to follow up and talk with Phil in Michigan State about the implications of this work. And in doing so, we ended up developing a partnership with MSU. They have unique and very critical technical capabilities for understanding nitrous oxide flux in corn production. They have been studying flux in corn production for many, many years at MSU. MSU is one of the only institutions in the United States, certainly at the time that we started this work, that's capable of measuring nitrous oxide flux actually occurring in farm fields, and this was critical for our project. And they have developed key testing infrastructure with actual commercial farmers on the ground in Michigan, and we were able to leverage those relationships with those farmers to actually work with developing the methodology and this approach on commercial farms. And very importantly, many of the agronomic results that are developed in Michigan historically can be generalized more broadly across a broad range of crop types, soils, and climatic regions across the 12 states of the North Central region. And the next slide. So we did this project in two major phases. The first phase, 2006 to 2009, really focused on fundamental scientific research to basically evaluate emission fluxes of N2O in corn production on commercial fields in agriculture, and to determine whether that initial curve that Dr. Robertson and his colleagues had developed in 2005 held true at farm scale. And we wanted to kind of validate that original finding. And once we did that, and I'm sure Phil and Neville will talk more about the sciences appropriately, we then decided to take that scientific work that turned out very, very closely aligned with the work that Phil had done early on and his colleagues, and then develop an offsets methodology based on those scientific findings. And so we did the R&D work in collaboration with Michigan State, and EPRI, our members, funded that work, and I've participated since 2006 with Phil and Neville in developing the studies that we did and in developing the methodology. Next slide. On the left, you'll see a number of participants who have participated in this project. The EPRI member companies who funded it, the research organizations, the offset standards that EPRI and MSU have worked with that include the Verified Carbon Standard, the Climate Action Reserve, and the American Carbon Registry, as well as the methodology validators. On the right in the graphic, what you see are, on the right side, you see the chambers that we used, essentially real-time chambers, 24/7, on smaller test plots that we also used on our project in conjunction with the larger farm fields. And these boxes open and close at regular intervals. They take a gas sample from above the crop. They take that gas sample and it's analyzed in this trailer you see on the right, and the data is telemetried to MSU's labs. On the left, you see the fields at Michigan State University at something called the Kellogg Biological Research Station, KBR. And the graphic at the bottom, the colored bars, they show some randomized field trials that were done with different nitrogen application rates on these fields, these test fields basically, and a similar approach was done on commercial fields as well. Can I have the next slide? And what you see here very briefly is simply the work that we did on actual on-farm. So we did 5 sites, 8 site years in different parts of Michigan. These were lands that were growing corn or corn and soybeans. They used conventional tillage. They had 6 different nitrogen fertilization rates, and they used what's called a static chamber methodology, where graduate students, an army of them, went out into the fields at particular times and under particular conditions, and essentially placed a box or a bucket over the growing corn, took out a gas sample, and that gas sample was then analyzed in Dr. Robertson's lab, and the N2O fluxes were measured there. You see in the graphic on the right a screenshot of an actual field. And these fields were commercially produced cornfields where the farmer managed everything on the field, except in this block. And this block of land in the lower left-hand corner was a block that was designed to be fertilized in a different way with different rates of fertilizer use in a statistically random methodology to be statistically powerful. And different rates of fertilizer, kilograms of nitrogen per hectare of land, were applied to different blocks within that larger 35-meter by 60-meter block. And ultimately, at the end of the year, MSU harvested this particular block of land by hand to measure the corn yields and compared many, many issues, nitrous oxide, flux, and a number of other values between the lands that were, quote, managed by Michigan State and those that were managed directly by the farmer himself. Now, meanwhile, all the other management done on the lands, including the parts that were specially fertilized, were all managed by the farmer, and the farmer had no knowledge really of which of the blocks were, like how they were fertilized at what rate and such. Can I have the next slide? One of the most important things about this methodology, and something we're very proud of at EPRI, is that all of the work we did to develop the methodology, the scientific research, and the methodology itself have all been published in the scientific peer review literature. As far as we are aware, the actual core protocol itself, which is in the article in the upper left-hand corner, is an article that was published by Neville and Dr. Millar and Dr. Robertson and a number of their colleagues, Peter Grace, Ron Gale, and John Hoban. As far as we know, this is the only offsets methodology globally, including the many hundreds in the Clean Development Mechanism, that were ever published as actual methodologies in the scientific peer review literature. And not only was the methodology published in the literature, but the field research underlying the methodology was published in the literature, as well as modeling that we did associated with developing the methodology. So we believed in doing this, we developed a very sound scientific foundation vetted by the scientific community before we took the methodology at the time to the various offset programs like the Verified Carbon Standard to actually operationalize that under the existing offset programs in the voluntary market. Next slide. At this point, this particular methodology, what I call the MSU EPRI nitrous oxide offset methodology, has now been approved for use in all three of the voluntary offset market programs in existence. The most recent one that you'll hear mostly about today was under the Verified Carbon Standard, and that's what we're here to talk about today. I just want to briefly mention a similar methodology was approved by the American Carbon Registry last July, and another methodology that's quite similar and based on the core parts of the MSU EPRI methodology also was approved by the Climate Action Reserve in 2012, and an updated version at the end of December 2012 that did some technical changes to the originally approved methodology. As far as we're aware, this particular methodology is the only one that's been approved in all three of these major offset programs. Next slide. Thank you very much for the time, and certainly if we have time for, we'll have plenty of time for Q&A at the end of the webcast. If you're interested in learning more about EPRI's role in offsets or in this methodology, by all means, I'm happy to address those questions. And at this point, I'm sure what you've all been waiting for is to hear from Dr. Robertson and Dr. Millar about the actual methodology, how it works, and what you have to do if you want to apply that methodology on farm.
Thanks, Adam. That was a very helpful overview of EPRI's engagement, but particularly a very helpful insight into the empirical and scientific research that underpins this methodology. Neville, Phil, over to you. Can you provide us an overview of the key elements of the methodology?
Hi, thanks, Edie. Yes, I hopefully can. Just by way of a preamble, and thanking Adam for his great overview of the project as a whole. My name's Neville Miller. I'm a senior research associate at the Kellogg Biological Station, Michigan State University, and one of the principal authors of the MSU EPRI methodology. Initially, I just want to take the opportunity to thank all the co-authors and collaborators on the methodology, and also I'd like to thank the organizations and individuals that commented during the public comment period, and the validation teams from ESI and DNV during the methodology approval process for the contribution. Finally, I'd also like to thank the funders of the work, primarily EPRI, but also Michigan State University Ag Bio Research, and the National Science Foundation Long-Term Ecological Research Program. So just for the first slide that you have up in front of you here, I wanted to supply just a quick reminder of the basics of the MSU EPRI methodology as it currently stands before getting into a few more of the details. The MSU EPRI methodology allows project developers to quantify emission reductions of nitrous oxide from cropland across the entire United States. This reduction in emissions, i.e. the generation of the carbon offsets, relies upon a reduction in the rate of nitrogen fertilizer applied to the cropland during the project period as compared to the baseline period. And depending on the U.S. state where the project site or sites are based, the calculations of N2O emission reductions are aided by one of two emission factors that link the rate of nitrogen fertilizer applied to cropland to subsequent emissions of nitrous oxide from the cropland. And they are a generally accepted Tier 1 emission factor. The use of the word tier is borrowed from IPCC nomenclature, or a Tier 2 regional emission factor generated from the empirical research in Michigan, which Adam has previously mentioned. And finally, to reiterate, the field research that underpins the methodology is publicly available in the peer-reviewed literature, again, as previously presented by Adam. Next slide, please. Thank you. Okay. So I just wanted to chat a little bit about the methodology guiding principles before we go forward. And these principles obviously relate not just to the methodology, but for the associated projects that we hope will be developed. They are initially a high environmental integrity. We want the credits generated from the methodology to be fungible and come with co-benefits, as Adam mentioned previously. And I'll expand upon that a little bit in a few slides. Again, we think it's vitally important to have a methodology based upon robust and defensible science that's ideally peer-reviewed and published in the literature in high-impact and widely publicly available journals and other outlets. We also wanted the methodology to be as non-prescriptive as possible. In other words, a methodology that does not mandate specific management practices or imposes strict eligibility criteria, but it allows the farmer the flexibility to achieve their end management goals. And again, I'll expand on this in a future slide. We wanted and believe the methodology to be transparent and practical. So to that end, we hope it represents an overarching approach to greenhouse gas emissions reductions that's easy to understand, containing equations that are straightforward to use. Strongly linked to those last two bullet points, we want the methodology to be suitable and of strong potential for project adoption, aggregation, and stacking, and for the methodology itself to be readily open to adaptation and extension. For this to be the case, the projects that use methodology should entail low effort and low cost, particularly with respect to the farmers and the data and documentation that they're asked to collect and provide, and the potential invasiveness that this involves. We also hope that the project should be simple to verify, important, for example, to aggregators or other accredited organizations. This is, of course, relying to a large extent on the methodology transparency, and this may help lead to a quick adoption potential. Due also in part to the near immediate project credit awards and the high frequency of the crediting cycle, for example, annually in a continuous corn cycle with one site. And obviously we hope this entails a broad uptake of the project as a result of the flexibility of the protocol to reduce the nitrogen rate through a variety of approaches. So in short, we want it to be the methodology and the associated projects to be easy to use and easy to verify. Next slide, please. So just before I chat a little bit about the key applicability conditions, I just want to mention more about these guiding principles. With these principles in mind, I think we can highlight two main categories of benefit that the methodology can provide, and those are environmental and financial benefits, both with multiple beneficiaries. From an environmental standpoint, using the MSU EPRI methodology will result in a reduction in the greenhouse gas footprint of agriculture in the U.S., specifically a lowering of the global warming potential of the cropping systems. But also there will be a reduction, as Adam mentioned previously, in the amount of what we call reactive N entering into the environment. By this I mean not just nitrous oxide, but also other forms of N, including N in ammonia, and nitric oxide, and nitrates that can pollute air, water, and soil. So in general, a reduction in N entering the environment means a reduction in N polluting the environment. From a financial viewpoint, there's an obvious benefit to the farmer who can reduce his fertilizer costs without reducing crop yield, and I'll talk more about that later. And it will also receive a financial reward through the carbon market for the credits generated. But also industry may benefit through the delivery of potentially large volumes of sought-after offset credits, particularly in the short term. So now on to the key applicability conditions. Fundamentally, the protocol is geared towards farmers who currently use external sources of nitrogen to fertilize their crops. The fertilizer types that are eligible are synthetic and organic, with all end inputs considered equal on a mass basis, irrespective of their source. With regards to fertilizer management, the fertilizer can be applied at any time during the cropping cycle. For example, before, at, or after planting. The application is in effect calendar year agnostic. Nitrogen fertilizer application management must adhere to the appropriate best management practices, the BMPs of the region. And that includes the timing, the placement, and formulation of the fertilizer. And also the N rate applied during the project period must be sufficient to generate yields similar to the baseline period. To demonstrate that, this will entail either a proven consistency with the most recent state or regional nitrogen rate recommendations, or a certification to that effect provided by a professional crop advisor. Next slide, please. Thank you. So for the nitrous oxide emissions included in the calculations, they are both the direct emissions, emissions that are emitted on site from the project site where the fertilizer is applied, or indirect emissions. Those are emissions off site, beyond the project site, but as a result of the fertilizer application on the site. And this includes nitrous oxide emissions produced in waters and soils as a result of, for example, nitrate leaching and ammonia volatilization. Next slide, please. The third applicability slide. Projects must be implemented in the United States only, as we've heard. Type 1, I'd call them, located throughout the U.S. All project lands in the U.S. and all croplands in the U.S. Those projects would use classified as Method 1, if you like, or Tier 1, which is in effect the IPCC global method, a linear relationship between nitrogen rate and nitrous oxide emissions, whereby 1% of the nitrogen applied is emitted as nitrous oxide nitrogen. There's also the Type 2 project, which, as mentioned previously, are located in the U.S. North Central region. Those are 12 states encompassing the Midwest and beyond. And for here, we're talking about corn in row crop systems, corn in rotation with other crops in these row crop systems. And they would use what we call method or Tier 2, which is the MSU EPRI derived nonlinear relationship between N rate and N2O emissions. And I'll show a little bit more about this on the next slide, please. So I'll just try to explain the slide. It's a little complex, but this is regarding the protocol accounting of the two types of method, two types of project that can be utilized from the methodology. It's a graphical representation of the comparison between the Type 1, in other words, the IPCC Tier 1 method for the US-wide use, and the Type 2, Tier 2 MSU EPRI quantification method for the North Central region. So on the x-axis, you can see there's N fertilizer rate in units of kilograms of nitrogen per hectare per year, and on the y-axis, you can see nitrous oxide emissions in units of kilograms of nitrous oxide nitrogen per hectare per year. We see there the dashed green line, the thick dashed green line showing there, it shows the Type 1 linear relationship, the global linear relationship where 1% of the applied N is emitted as nitrous oxide nitrogen. The solid red curved line, the exponential line, is the MSU EPRI nonlinear relationship found as a result of the empirical field work conducted in Michigan. And if you see also there's a vertical dotted line, dotted black lines, those represent the reduction in an example of a reduction in N rate from a hypothetical baseline scenario to a hypothetical project scenario. So you see in this case it's approximately from about 180 kilograms of nitrogen per hectare per year to about 120, a reduction of around 60 kilograms of nitrogen. And if you notice where those two vertical black lines intersect with the Type 1 linear relationship and the Type 2 nonlinear relationship, you see drawn alongside those intersections the two dotted horizontal green lines and the arrow. As a result of that, they represent the accompanying N2 emission reduction if the Type 1 linear IPCC quantification method is used to reduce nitrogen rate on the field. And the horizontal dot dash red lines, thicker red lines, and arrow represent the accompanying N2 emission reductions if the nonlinear type 2 MSU EPRI quantification method is used. So as you can see, for an identical N rate reduction, the accompanying N2 emission reductions from using the MSU EPRI nonlinear method can be substantially greater than when using the linear method. But both are eligible for projects depending on the geographic location. So these additional, if you like, so to speak, N2 emissions from the nonlinear relationship result in a larger number of offset credits and may actually further incentivize N rate reductions in project participation in the North Central region. Next slide, please. As mentioned earlier, the MSU EPRI methodology is as non-prescriptive and flexible as possible with regards to the eligible management practices a farmer can adopt or change to reduce N fertilizer rate. On the slide are some examples of the approaches a farmer can use to reduce N fertilizer rate. These changes or adoption of these management practices can be required maybe through adherence to local or regional fertilizer best management practices, but more likely they would represent, if you like, an innovation beyond these requirements. So for example, more accurate estimates of the nitrogen needed by the crop using economic optimization calculators, such as the maximum return to nitrogen or MRTN approach, currently, but only relatively recently, being recommended in a number of the US Midwestern states. And I'll talk a little bit more about that in a later slide. Obviously, the timing of N application, for instance, a shift to spring rather than fall N application, may allow a reduction in nitrogen rate during the cropping cycle, or a split application in the spring with a separate base and side dress application. The source of nitrogen fertilizer, obviously important. In other words, the formulation, liquid, solid, gas, etc., can be altered, and also whether the fertilizer is formulated for slow release or used in combination with nitrogen inhibitors. The formulation is closely linked to the placement of fertilizer, such that the desired formulation to some extent dictates the placement required, and vice versa. And techniques such as surface broadcast or disking into the soil are common in this regard. Also, placement can be tied in with the limited but increasing use of precision agriculture. By that I mean the use of machinery and techniques that can apply specific amounts of fertilizer to specific points in a field that can reflect the plant uptake potential. The management practices covered by those first 4 bullet points have been termed the 4 R's, the right rate, the right timing, the right source, and the right placement. But another good example is also the potential to use cover crops. For example, the use of a winter cover crop may take up the residual nitrogen left over from a previous summer crop. And this nitrogen, which may be released during the decomposition in the following year, may reduce the amount of external N fertilization needed in the spring and summer to grow the subsequent cash crop. In any case, ultimately the aim is to give the farmer flexibility in the choices to manage the field and to give a greater confidence and lower risk to the decision-making process for reducing nitrogen fertilizer rate. Irrespective of the choice of N management practice or practices adopted or altered, the integrated result is a lower nitrogen rate and a reduction in nitrous oxide emissions. Next slide, please. So I just want to talk about some of the key issues that we have to consider during the development of our protocol, and indeed all of FOLO protocols. Those are baseline determination, demonstrating additionality, dealing with permanence and reversal, proving no project leakage, and dealing with uncertainty. And I'll spend a minute or two now on each of those issues talking about how the MSU EPRI protocol dealt with them. Next slide, please. Thank you. So here I want to talk specifically about the determination of the baseline N rate, which is the only determinant required for estimating baseline nitrous oxide emissions. The baseline nitrogen rate in the MSU EPRI methodology can be determined using one of 2 approaches. Both approaches require at least 5 years of records. This length of historical record required depends on the project crop and the rotation history of the project site. Approach 1 uses some site-specific management or farmer records. These can include nitrogen fertilizer purchase records, application rate data, manure application rate data, manure and content data, etc. Approach 2 uses county-level records and calculates the baseline N rate from crop yield data derived from the USDA web pages and relevant regional state equations that are based on yield goal estimates. As you can see, approach 1 is preferred due to the finer spatial resolution and the more potential offsets that can be generated. But if approach 1 cannot be used, approach 2 can be used, where, as I say, the county level data can be used to generate baseline N rates. Next slide, please. So demonstrating additionality. Additionality to VCS in this methodology is assessed using the performance method. There are 2 tests, if you like, in this performance method: a regulatory surplus test and a performance benchmark test. As we probably know, for the regulatory surplus test, there must be no mandatory law or statute or other regulatory framework in place that requires the producers to reduce their fertilizer rate below that of a business as usual scenario. With the performance benchmark, farmers must reduce their nitrogen fertilizer rate to below a threshold that represents the business as usual rate. This is defined in terms of nitrous oxide emissions and megagrams of CO2 equivalent per hectare. This business as usual rate is based on the historical yield goal approach and has been shown to be common practice throughout the region and the US in general, and that's identical to the calculated baseline N rate of the project using either approach 1 or approach 2. Next slide, please. So dealing with permanence and reversals, Adam's mentioned beforehand, I'll reiterate, here permanence refers to the potential for the reversal of greenhouse gas reductions and removals. The permanence issue is not relevant for some project types since the emission reductions occur at the time that the technology is put in place and they're irreversible. And this is the case with projects that use the MSU EPRI methodology, where the avoided N2O emissions due to a reduction in the nitrogen fertilizer rate occur immediately, are irreversible and permanent. So there are no permanence or reversal concerns with the MSU EPRI methodology, and as a result, no risk mitigation mechanisms are required. Next slide, please. So demonstrating no project leakage. Land is maintained in the crop production prior to implement the project and afterwards. So the project developer is going to provide proof of land use and crop rotation as a part of the required management records for project verification. In the absence of the project activity, the continuation of these practices using the business as usual nitrogen management practices are the most realistic and credible scenarios. With no crop yield reductions expected, and I'll get onto that in the next slide or two, due to the project implementation, there's no incentive for any market leakage or activity shifting. Next slide, please. So on this slide, I'll show an example of an economic approach to nitrogen rate management, and I'll show how yield reductions do not occur with well-considered nitrogen rate reductions. So on the slide are 2 screenshots from a web-based application from Iowa State University Extension that can calculate the economic optimum N rate application to corn in 7 of the U.S. Midwestern states. At this time, those states are Iowa, Illinois, Indiana, Michigan, Minnesota, Ohio, and Wisconsin. On the left screen shows where the state or region can be chosen and where the N fertilizer price and corn price are entered. The right screen shows an example of a yield response to N rate graph generated from, in this case, Michigan data for a corn-soybean rotation at a nitrogen to corn price ratio of about 0.10, a very typically representative ratio over the last few decades. The gray vertical band you can see on that right-hand graph shows the profitable nitrogen rate range for corn that can be applied to the field. In this case, it's between 120 and 138 pounds of nitrogen per acre, or approximately 135 to 155 kilograms of nitrogen per hectare. And the red star there shows the MRTN rate. In this case, for Michigan in that system, it's about 127 pounds of nitrogen per acre, or around about 140 kilograms of nitrogen per hectare. So you can see that if a farmer is, for instance, currently fertilizing at about 175 pounds of nitrogen using a typical yield goal approach, this economic analysis can give him some confidence the reduction to, say, 150 pounds or a little lower will not reduce yield, and that even a reduction to 120 pounds may have a negligible yield impact. So, of course, increasing these N rate reductions would save increasingly larger amounts on money that would have been used to fertilize the fields. In this example, a change from a typical yield goal approach to an economic optimization approach for N rate application will provide the farmer the opportunity to reduce N rate without reducing his yield. This calculator or calculators similar to this can be useful tools for farmers who may want to participate in N2O reduction projects by providing them with a quantitative estimate of the yield impact a particular nitrogen rate reduction would have, and along with other considerations that may provide a greater degree of confidence for changing nitrogen rate practice. As mentioned, this economic approach is only one of the many options a farmer would have to lower nitrous oxide emissions when using the Michigan State EPRI methodology without impacting the crop yield. Next slide, please. So there's a general concern in the offsets arena, I would say, about the uncertainty associated with greenhouse gas emissions from agricultural systems. And this in the next slide, I'll try to overview how the MSU EPRI methodology has successfully dealt with this issue. At the top of this slide, you can see a simplified equation showing how project emission reductions are calculated. You can notice the red U and C component of the equation at the end, which represents the inclusion of an uncertainty deduction factor associated with the project emissions. And the graph on the bottom left shows an example of an N2O response curve to increasing N rate. On that graph at the bottom left, the solid line in the middle represents the N2O response, and the dotted lines on either side represent the 95% confidence intervals generated. And you can see that the uncertainty around emissions increases as we increase the N rate, and that's reflected by the widening of the dotted lines as the N rate increases. But that's okay. We can quantify this uncertainty and the uncertainty around emission reductions using statistical techniques. And in the MSU EPRI methodology, a Monte Carlo bootstrap method was applied to the empirical data we collected on the commercial farmers' fields. From that, we derived an equation that can be used to calculate the percentage of uncertainty associated with emissions reductions in a project. Next slide, please. And this uncertainty percentage is related to, on our methodology, a set of available conservativeness factors from the UNFCCC and IPCC, and these can be used to assign uncertainty deduction factors. These deduction factors are then plugged back into the equation from the previous page, and you can discount the number of offset credits awarded to the project. In short, the greater the uncertainty associated with emission reductions, the greater the deduction. However, we believe that even with a relatively high project uncertainty, the credit deductions are not so severe that they would act as any barrier to prevent project implementation. Next slide, please. So I'm coming to the last two slides here, and just some brief information about the monitoring and information needed during a project, and some examples on the next slide of a project, a pilot project that we're actually hoping to be verified very soon. Some simple information that would be required, and we've already covered quite a lot of this, but crop type and rotation on the project field, some field coordinates, some files that depict the shape of the field, etc., some proof of ownership of the field itself, of the project site, or the ability to rent that site, and an affirmation from the owner that everything is going to be okay. Some simple application rates and dates, some from load sheets, fertilizer load sheets, or from nitrogen maps where, for instance, maybe more precision agriculture has been applied. And you can see examples of those documentation on the right-hand side. Next slide, please. So I believe this is the last slide I have. It's in relation to, as I mentioned, an associated project. We have a proof of concept project, which we started off in 2011, which will hopefully go to 2015, based in Tuscola County in Michigan. This is on, again, a commercial corn farmer's field in the year 2011, and this year, and in 2015, he will be reducing his nitrogen rate applied to his corn by roughly 15 to 20% on a field that he has designated for use, roughly a 40-acre corn field. The project verification and the offsets transaction expected from this project are due in sometime spring or summer 2013. And that transaction would, in effect, represent the world's first trade, we believe, of carbon credits derived from agricultural nitrous oxide emissions reductions. And so I believe that's my last slide, and with that I'll thank everyone for listening to you and pass it on to Aditi and Environmental Services, Inc.
Thanks, Neville, for providing a very thorough overview of the methodology and the key elements of the methodology, particularly the overview of how the two emission factors work, IPCC default and the region-specific CO2 factor. With that, I'd like to pass this on to Sean from Environmental Services. Sean's going to be presenting an overview of the issues that need to be considered when validating and verifying projects that are developed under this methodology.
Good afternoon. This is Sean McMahon, and I worked as the lead validator and verifier for the methodology. I work for Environmental Services Incorporated. We're a full-service environmental consulting firm that was established in 1986. We're accredited by ANSI under ISO 14065 to conduct validations and verifications worldwide at the project level for land use and forestry. Richard Scharf, who was also critical to the validation process, and he was one of the primary soil scientists on the methodology validation. He's also on the line to answer questions during the Q&A. I'd also like to say a quick thanks to MSU and to ESRI for selecting us as the validators, as it is an exciting methodology, and we very much enjoyed working on it. Okay, for my portion of the discussion, and I see the next slide, that's great. I'm going to take just 5 minutes to quickly touch on some basic elements that we'll consider when validating and verifying projects under VM22. Just a note to define validation and verification at a very high level. Validation is essentially the process of confirming that the project description and the documentation complies with VCS rules and the requirements of the methodology, whereas verification is primarily confirming that the project was implemented in accordance with the validated PD, and also to ensure that the emissions reductions were quantified appropriately. Regarding the methodology itself, it is indeed fairly straightforward, and that's kind of the critical element here. The additionality demonstration for regulatory surplus, it's demonstrated as was stated through compliance with local, state, and federal laws, and the performance benchmark is established through records. Unlike many of the other methodologies that we work with, the actual activity itself, which is a reduction in the rate of nitrogen applied to cropland, will be confirmed through records and the application of accepted emissions factors. There will be site visits. The site visits will be required to confirm project boundaries and baseline conditions such as cropping type, adherence to best management practices, lack of histosols if the NRCS mapping is insufficient, and then the other applicability conditions. Again, for verification, we're not observing or measuring the actual reduction of nitrogen application in the field, as this is going to be done through the desktop review of the records and the calculations. As indicated earlier, if option 1 is selected, much of the review will be dependent upon the farmer's records, which of course will vary from project to project. From a verification point of view, there are 2 primary ways to make kind of non-conservative errors in these records. The first is to overstate the baseline application rate, and then the second would be understating the project application rate. And these would be 2 areas that will be pretty closely scrutinized during the verifications and the validations as well. All assumptions will need to be fully justified. For example, if a farmer only enters part of his or her operation into a project, and we're looking at the fertilizer purchase receipts for the entire operation, the PD will need to account for all of the fertilizer. And this could potentially require a detailed look at part of the operation not within the project boundaries to account for the fertilizer. Next slide. Okay, some key areas here. Of course, the farmer's record-keeping habits will vary, as I stated, from time to time, from project to project. You know, from they keep it all in their head to very meticulous and detailed record-keeping. When the preferred approach 1 is used, there could be some debate about what constitutes sufficient evidence, especially in cases where only part of a farmer's operation is included in a project. There's likely going to be other yet unforeseen scenarios that will kind of blur this line, and we'll expect VCS will continue to develop guidance on this as these scenarios pop up. Guano management techniques are specified by the methodology for nutrient management projects. It's likely that they will be used in order to meet the desired crop yield. If they are used, the discussion of the newly adopted techniques and some corroborating evidence that these practices are being used will go a long way to support the validation and the verification. If special equipment is purchased or rented for fertilizer placement, or farmer contracts for special services related to new techniques, copies of receipts or contracts would be important. Of course, statements from NRCS staff or licensed or certified crop consultants and advisors could also be very important for the corroboration of the records in support of the project. That is a very quick overview, and I know we only had it for 5 minutes. So what we'll do, Richard and I will be available for the Q&A. So I think I'll hand it back to Aditi.
Thanks, Sean. That was a very helpful overview of what to look out for in validation and verification. So with that, we will move on to the Q&A session. If you haven't already done so, please send us your questions. You can type in your questions into the chat box that's available on the software, and we've also been collecting questions throughout this webinar. If we do not get to your questions in the course of today's webinar, we are happy to follow up with you offline, so you can always email us your questions separately as well. And a copy of this presentation will be available on the VCS website, and we will post that for the next week or so. So with that, I will pass it on to Ben Block, who will be moderating the Q&A session, and he will be taking up specific questions that came up from the participants during the webinar.
All right, thank you, Aditi. And to second one of the points that Aditi made, and in response to a question we already received, as Aditi said, a video of the webinar will be posted on the VCS website. You can just look on the page of the website for this methodology, and you'll find the video there. So first, actually, a question for Aditi. It was mentioned during the presentation that this methodology has also been approved, or a version of this methodology has been approved through the Climate Action Reserve and also through the American Carbon Registry, ACR. And so there was a question about what specifically are the differences, or generally how are these methodologies different from one program to the next?
Thanks, Ben. So functionally, the three methodologies under the various programs, VCS, ACR, and CAR, are similar, are largely similar, though there are certain specific differences. The VCS methodology, one of the issues we focused on was on providing more transparency and justification around how the performance benchmark was developed, which is essentially how do you justify that the business as usual scenario is an appropriate benchmark. And we required more transparency around that in line with the VCS framework for standardized methods. In addition, the VCS methodology is restricted to the United States. I believe the ACR methodology is applicable globally, though they may have some caveats as to how it's applied outside the U.S. And I think the CAR methodology is restricted to the North Central region, if I'm not mistaken. But perhaps Neville and Adam are better positioned to answer this question because they have been directly involved with the development of this protocol under ACR and CAR.
Adam, do you have anything that you want to add to that response?
Sure. Thank you very much. It's an excellent question. I think Aditi hit some of the high points. The ACR methodology is potentially globally applicable. It's done in a modular way, and the only module that's currently been approved is the use of the Tier 2 approach in the 12 states of the North Central region, although there is a mechanism within there to broaden its use either from Tier 1 or Tier 2 by parties who bring specific data sets to the ACR and make a case to the ACR directly about the applicability of a Tier 1 or Tier 2 approach in a particular region for a particular crop. That could be done in the United States or internationally. One of the other key differences in the VCS, it does require a farmer under the VCS methodology to obtain essentially a written certification from a party, whether it's USDA, a suitable crop scientist, or the Ag Research Service, or qualified university agricultural consultant, an expert party that the amount of fertilizer they're putting on their land is sufficient to achieve the yields that they have on average achieved during the baseline period. The VCS was one of the validators who had a concern that somehow farmers would, dramatically reduce their nitrogen fertilizer use to essentially just do offsets and no longer produce their crop. While this is economically is very, very unlikely, it doesn't really make a lot of sense. We understood the need to have some kind of outside third body give a certification, and that's built into this methodology. One of the other important differences on the CAR side, as many of you know, CAR develops its own methodologies. It puts together a stakeholder group, and it has a fundamentally different process for developing methodologies than the VCS and the ACR. And so some of their built-in eligibility and their particular performance approach differs from the one that's used in this methodology. But the core quantification method, the use of the Tier 2 emission factors approach in the 12 states of the North Central region, is identical across all of the methodologies. I'm sure Neville probably or Phil want to add a few points here as well, but I think those are the big differences.
Neville here. Yeah, no, I think you've covered the major issues there, Adam. Not really too much more to add. Again, the data sets from the ACR can be either in the U.S. outside the North Central region, or indeed within the North Central region if it's a crop other than corn, and indeed they can be outside globally in maybe Mexico or China, depending on where data sets are becoming available. And we believe there's sufficient literature for projects to be adopted in countries outside the U.S. It just would take a project team to bring them to the ACR's attention, or indeed the VCS's attention for future methodologies to try to get them verified.
I would add, this is Adam, one of the important advantages of the verified carbon standard methodology is that it is applicable across all crops and all regions of the United States. The other two methodologies are limited to simply the North Central region, where the vast majority of nitrous oxide emissions do occur. But the VCS methodology using the Tier 1 approach could be used for any crop in any region, including crops grown in California.
Thanks, Adam. So building on Neville's response there, we have received several questions about why the methodology is only applicable to the United States. So Neville, could you speak a little bit more to the data set limitations that that are the rationale for limiting this methodology, or other reasons perhaps why the methodology is only applicable to the United States? In particular, we did receive one question about why the methodology is not applicable to Canada, or what steps might be taken in order to expand the methodology to include similar regions in Canada.
Well, with regards to the global data set, we believe that there is the opportunity for projects to be adopted outside the U.S., and we, from a starting point, attempted to do that across the board. That some others at VCS and other organizations may speak to the fact as to why the limitations were there. I can speak to the fact that some organizations, individuals weren't totally accepting of the fact that every single site and every single crop could be shown to have an emission factor of 1% as a conservative value. We went down the line with other organizations looking at positive lists and trying to identify particular crops and regions that may have that emission factor suitable. We believe it's more globally widespread, and so there's no real problem for us if these projects were adopted in various parts of the world, including Canada, where they have a pretty rich data set for nitrous oxide emissions. So hopefully future iterations of the methodologies, both the VCS and the ACR and the CAR, will include projects that can be outside the U.S. and including Canada.
Great, thanks. So we've, to change topics slightly, there have been some questions that we received about specifically the best management practices that would need to be undertaken as part of the project activity. We have one question about whether organic farming practices could be among those activities. So maybe just elaborate a bit more, Neville, on what practices specifically you're envisioning in the project that you're working on, and what other activities could be applicable under the methodology?
Well, I mean, the best management practices we had in mind here, when we, in particular to the VCS, we were thinking along the lines of the other 3 R's for the most part. We were thinking more of the lines of good formulation of fertilizer, good timing of fertilizer, good placement of fertilizer. And these are not necessarily mandatory regulations at state or regional level, but these are guidelines that a lot of states and regions have in place for good fertilizer management. So it would be necessary to show that these considerations were taken into effect during an overall, if you like, nitrogen management plan that the farmer had. One maybe obvious example, but there are many, is that depending on the application of manure in the fall, may not be appropriate in the certain conditions if the soil and environmental conditions are not appropriate. And so maybe the manure application in the spring would be required in order to make the project more suitable. But that is not a general approach. That it is really specific to the conditions and the management practices in place in the region or the state.
This is Phil. If I could elaborate a little bit on that, Neville.
Sure.
The best management practices are a fairly broad spectrum of allowable practices within any given set of agricultural management practices. And with respect to nitrogen fertilizer, the practices generally are regional, and they often are legislated, and as a way to allow farmers to avoid nuisance suits in particular. But they do differ regionally, and for example, fall fertilization is considered best management practice in some parts of the Midwest, but in other states it's not considered best management practice. And so well, to meet the best management practice guidelines, one would need to know what the specific state requirements are. But they tend not to be particularly onerous. They give farmers a wide latitude in fertilizer application and technologies.
So building on that point, Phil, there was one question we received about the extent that farmers are over-fertilizing. The question is that they heard that because of the rising cost of fertilizers, most farmers in the region where this stakeholder was talking to farmers heard that they no longer over-fertilize. So to what extent are we seeing over-fertilization, and how does that vary by region by region? So as you were saying, the management practices would depend on the region, but specifically as far as to what extent there's a gross amount of over-fertilization, how are we seeing that vary across the states? And it would be interesting to hear the perspective of the verifiers as well, who are going on the ground and seeing these sites. So maybe Phil, first, you want to respond?
Sure. Over-fertilization is, of course, to some degree in the eye of the beholder, and it depends on the technology available for assessing how much fertilizer needs to be applied. So that a farmer with the best technology might apply one rate, and another farmer might with less sophisticated technology apply another rate. Neither would necessarily be over-fertilizing per se. Rather, the farmer who has and is applying the best technology has a better and more precise estimate of the amount of fertilizer that's needed, and so we'll be able to apply less for that reason. And so we tend not to think about this in terms of over-fertilization as much as better, more precise applications of fertilizers, and in that way reduce the amount of fertilizer that's otherwise applied. So, and those who have looked closely at the issue of over-fertilization per se will recognize that it's a very difficult measure to quantify. We don't collect much data in the U.S. on the amount of fertilizer applied at the field scale, and so we don't have a good feel for how much many farmers are actually applying. Our methodology is based on the premise that whatever amount of fertilizer is being applied with additional technology and innovation, most likely every farmer can fertilize less.
If I can just add to that, Ben, so this was one of the issues that came up when this methodology was being assessed under the VCS. As many of you may know, the VCS has requirements for performance methods, which entails setting out very transparent criteria for why a certain benchmark level has been chosen, why a certain level has been chosen as the performance benchmark level. So a question that we asked was, why is the business as usual scenario, the threshold under the business as usual scenario, the benchmark level? And essentially is related to this question of how do you know that most people are over-fertilizing. So this justification is now provided in the annex to the methodology, and as Phil pointed out, there isn't enough research or data out there on the actual rates of fertilizer application, but there are some studies which talk about the predominant approach in the U.S. being the use of the yield goal approach, which Neville was talking about earlier. And so the argument is that given that the yield goal approach continues to be the predominant approach to applying fertilizer, there are opportunities for optimizing the rate of fertilizer application. Neville, perhaps you could elaborate a little bit on the justification provided around the use of the baseline business as usual scenario as the performance benchmark.
Thanks, Aditi. Well, in part, you did just explain that. I mean, here when we're trying to develop this test for additionality, we wanted to make it, if you like, almost site-specific with regards to farmer records, but also encompassing the sector of general approaches. And as you mentioned, the yield goal approach has been in place for many decades as a tool or a means in some shape or form to make estimates of N requirement for the future crop based on previous yields. Relatively recently, although still a few years ago, that way of estimating N rate recommendations has been shown to be inaccurate and to some extent quite invalid. Not a good predictive tool, but as a means of a simple tool, it certainly is still used by, from what we understand, a large percentage of farmers, both from data sets that we've collected in Southwest Michigan and from larger scale data sets, although they're not entirely complete at the larger state, federal level. So this common practice, if you want to call it, this yield goal approach is really a sectoral approach, and it's continually shown to be used and continually recommended as an approach, even though better methods are out there. So we feel it's a very good approach, not just at the small site-specific scale, influencing farmer records. It's also a sectoral approach, and for that reason, it seemed the most appropriate way to cover a large area, but at the same time have site-specific records being used to justify it.
Great, thanks. And over to Sean and Rich from Environmental Services. Do you want to just contribute your opinions as part of the assessment team on how you all assessed and reviewed the best practice approach and compared that against the common practices that are underway on farmlands across the country?
Well, it is it's a determination that would have to be made locally. What business as usual would be, baseline would be, well, you know, from what I have seen, there is plenty of room for reduction in the use of nitrogen fertilizers in many areas. So, you know, the statement that there is no over-fertilization is I don't know if that's a statement that could be justified.
And this is Sean, and so I think, and of course it hasn't been implemented yet, but this was part of the consideration, that that using kind of the county level records and other records if available as a basis, records that exist outside the project. But I think that's going to have to be part of the project proponent's job to do the demonstration that it is a common practice. It's not, frankly, I'm not thinking of any other alternatives offhand, so if any of the methodology developers are thinking of any there, they could identify them, but ultimately it will be up to the project proponent to kind of put the argument in front of us.
Thanks, Sean, Rich, for your feedback. So it's past 2:15 here on the East Coast, and we've now been over an hour with this webinar. So I think we will wrap it up. As I mentioned before, if we could not get to your questions, we will try and get back to you offline. In the meantime, do feel free to send us any further questions or feedback you may have on this methodology. You can email us your questions at the secretariat@vcs.org. But I'd like to thank everyone for participating in this webinar, and in particular, I'd like to thank the panelists, Adam, Neville, Phil, Sean, and Richard. Thanks for your participation.
Thanks all.
Thanks a lot.
Thanks all.
Thank you.
Yes, thank you very much.
Sure.
And thank you, Aditi and the VCS, for all the work you've done with us over the last few years to work on the methodology and help us get it into shape so that it could, you know, that we could answer all the questions that were required and get through the process. It's very helpful.
Welcome.
All right. Thank you all for joining. Bye-bye, everyone.
Thanks, Ben.
Bye.
Thanks, Aditi. Bye.
Bye. Bye.